Hello everyone, welcome to our talk on DeepSIM, GPS spoofing detection on UAVs using satellite imagery matching. My name is Nian Xue from New York University. Today, I'm very excited to share our work with you. First of all, let me begin by giving you some background. UAVs, also known as drones, in recent years have played a significant role both in industrial and commercial areas. Although there are different kinds of UAVs, virtual sensors, for example cameras, have become a standard device for UAVs. Nowadays, UAVs have been widely used in many scenarios such as aerial surveillance, military reconnaissance, and disaster monitoring. For example, in 2011, a Honeywell drone was used to investigate the radioactive reactor after the destructive earthquake in Fukushima, Japan, where humans cannot approach. Although UAVs has many strong benefits, a few risks have gradually appeared. According to a recent review on aerial vehicles, we can find that UAVs are facing many challenges in the real world. One of the most pressing issues is the GPS spoofing attack. A famous example is the Iran-US RQ-170 incident. To illustrate such attacks more easily, we simulated a GPS spoofing attack to manipulate the GPS location of our drone. As we can see, the drone, which was originally in Suzhou, China, was tempered to just above the Empire State Building in New York City. Spoofing attacks on UAVs in the real world motivate us to reconsider this problem. We propose the DeepSIM, which aims at detection spoofing attacks under the context of UAVs, which is an outbound method. Specifically, we use the deep learning model to analyze the similarity metric from a virtual perspective. Compared with the traditional methods, our method is easy to deploy, and there's low need to modify existing GPS infrastructures, and UAVs can detect attacks independently while flying. Let me briefly introduce the detection process. The UAV receives GNSS data from the satellite. Suppose that a spoofer is sending fake GPS signals to the UAV. The UAV then takes photos and sends it back to the UAV controller or the ground station via the communication channel. After receiving the photo that contains fake GPS data, the controller extracted the corresponding satellite imageries based on the data from Google Earth, and then feed the true images to the neural network. The neural network determines whether the two images pair match each other or not, and raises or not if two images are unpaired. In fact, this approach contains several challenges. For example, images taken by UAVs differ substantially in resolution, rotation, and quality. Besides, how to deal with ephemeral objects and historic satellite images is challenging. To validate our approach, we first need a dataset. We constructed a dataset named SatUAV that includes paired satellite images and aerial photos. We collected aerial photos from certain places in Asia and Europe using our own UAV. We also leverage existing aerial photos from the SensorFly website to enrich our dataset. Let's have a glance at this table. It summarizes the specification of the dataset we constructed. This dataset has already been released on the internet for further research. It's worth noting that the raw aerial photos need to be calibrated to construct a dataset. We adapted a central projection method to calculate the corresponding coverage. Ideally, The drone's camera needs to take photos as vertical as possible to get the GPS position. However, in practice, due to some reasons, for example, the mechanical limit or wind disturbance, it is very hard to be perfectly vertical. Thus, we introduce a calibration algorithm to reduce error. The black arrow indicates the actual projection, and the red arrow indicates ideal projection. Here are some examples of paired images after calibration. We can find that aerial photos and satellite images are very similar to each other. Now I'd like to move on to the system design part of the presentation. First, let's have a look at the attacker model. Here is the UAV that can receive GPS signals correctly. Then we consider an attacker sending fake GPS signals to the UAV by injecting, modifying, replaying, or delaying GPS signals. As a result, the target UAV will compute a wrong geolocation under spoofing attacks. In addition, the attacker may block or jump the communication channel between the UAV and the ground station by active signal transmission on the frequency channel. This would cause the UAV to lose contact with the ground station. Next, we present our neural network architecture. There are two models. That is an on-ground model, which is run by a central controller, and the on-board model, which can be excluded on the UAV. The biggest difference between the two models is the background neural networks. The on-ground model uses ResNet34, whereas the on-board model uses SqueezeNet due to its limited computational power. The original image is converted to an 8x1x1 feature map after a series of layers, such as full connected layer, batch normalization layer, and ReLU layer. The whole neural network is called the SIMS network, which is widely used in face recognition. The aerial photo and corresponding satellite images are fed into the SIMS network at the same time, and then converted into the feature maps as mentioned previously. The SIMS network tries to learn the features so that if two images are paired, their Euclidean distance is small. This goal is achieved by optimizing its loss function, that is the constructive loss, which is shown below. By comparing the distance of two images with threshold, the deep learning model can detect spoofing attacks. Specifically, if the distance is larger than the threshold, there is an attack. Okay, now let's have a look at the experimental result. The two figures show the ROC curves, AUC scores, and training loss. It took about 13 hours to train the models. As we can see, after 20 epochs, the loss becomes stable. The first table shows the experimental result on the raw data set. The accuracy and F1 score are approximately 90%. We also measured memory usage, disk usage, and power consumption. For the time complexity, the on-ground model merely took less than 0.1 second to give the prediction. On the other hand, the on-board model needs about 10 seconds to do the inference task due to its limited computational resources. We also conducted an error tolerance test by shifting the photos from the original position. We found that as the deviation grows, DeepSIM is proved to think such deviation is due to GPS attacks. To further improve the performance, we adapted the data augmentation technique. We augment the data by 8 different methods. For example, rotation, grading, cropping, blending, flux, clouds, etc. Both models benefit from the augmentation technique. Finally, we got a success ratio of about 95%, increased by 5.3 percentages compared to the models trained on the raw dataset. To study the generalization ability of the proposed models, we collected extra test data from 4 places in the UK: Birmingham, Coventry, Liverpool, and Peak District. We got similar F1 scores on both models, which indicates that both models have good generalization ability even for unseen places. After spoofing attacks are detected, we give 3 countermeasures. The most promising solution is called return to home, which has been deployed in some UAV products. That brings us to the end part of my presentation. The source code and dataset are publicly available at our GitHub project website. The link is shown as follows. Now, I summarize the key points of our work to conclude this talk. First, we constructed a dataset composed of satellite aerial image pairs. Second, we proposed DeepSIM to detect GPS spoofing attacks. Third, we implemented a prototype and evaluated its performance. Last, we designed on-ground and on-board models for 2 different scenarios. That ends my talk. For more details, welcome to read our paper and give us feedback. Thanks for your attention, and feel free to ask if you have any questions.